Thank you, Bulbul, for the introduction. And first of all, I would like to thank the organizer to give me this chance to present this talk. And I will talk about the characterization of the dense jammed pattern, in which I will focus on the mutual relationship among the shear-jammed fragile state and the discontinuous shear thickening. Okay, so I'm from Kyoto. Kyoto is here, which is the old capital. So if you have a chance to visit Japan, please come to the Kyoto. And this is a Kamigamo Shrine, so which has a sand mountain, so which is one of the target of my research. And about the relationship between my research and the entropy, because this program is named from entropy information and order in soft matter physics. So I needed to connect my research with entropy. And I have written some paper on the entropy, non-equilibrium entropy, which is governed by the Berry-like phase. And so if we have two control parameter in the system, you may have a Berry curvature in the system. According to this, the Berry-like phase in a non-equilibrium system might have a path-dependent entropy. That is one of the interesting subjects in the relation to the entropy in a non-equilibrium system. But today, I would like to talk about a different subject on the dense granular materials. And some part of my talk is dedicated to the dense suspensions. Okay, so this is the contents of my talk. So firstly, I would like to introduce my talk and review on the rheology of the dense jammed matter. And this is the second part, is the main part. I will talk on the shear jamming of the frictional grains and the associated shear. And I will also discuss discontinuous shear thickening and fragile phase and the discussion. And if I allow the time to talk about the other topics, I will talk on the pressure control case, what is the difference between this volume control situation and the pressure control situation. And I will also talk on the difference between the linear response discussed here and the nonlinear response discussed here. And I want to talk about the suspension case, in which the hydrodynamic interaction plays an important role in this part. And I will conclude my talk in the last part. So, as you may know, if we have dense disordered particles or consistent disordered particles, including the vehicles, so the particle cannot move freely. So, and the typical target might be the colloidal glasses or sand castle. And of course, we can talk about the vehicle motion, the traffic flow. So in such systems, we may have a transition between the freely moving or ergodic moving phase and almost jammed phase, in which the particle cannot move at all. So, and this is a very famous phase diagram proposed by Liu and Nagel 20 years ago. So, in which there are three axes. Which is one of which is the density, mass density, and this is load, and this is temperature. So they can talk about the jamming and the glass transition in a unified way. And the most important one, characterization of the jammed or glass phase is to have a rigidity, as in the yesterday's talk about the critical point. And the jamming transition might be very similar to the glass transition. And about 5 years ago, Ikeda, Bercher, Jorge proposed a different phase diagram in which the temperature and Born fraction and stress, yield stress. So you may find the crossover from the final temperature glass transition to the jamming transition, but still we have a very different characterization of the jamming transition at type t equals 0, because the t equals 0 doesn't have any equilibrium situation. So equilibrium basis doesn't exist at the t equals 0. And the glass transition is a controversial fit, whether this is a actual transition or not, but the jamming transition has a definite similarity at jamming point. So, and that even when we focus on the jamming transition at t equals 0, this is a nice picture proposed by Liu-Nagel for the frictionless grains. So we have a critical jamming density in the horizontal axis, and this is a shear stress. So this part is unjammed phase, and above the critical density, we may characterize this phase as jammed phase, so which has a finite rigidity. But 7 years ago, including the Bulbul, if we are interested in the dense frictional grains, that such simple phase diagram is no longer valid. So we have more rich structure in the system. So there is a shear-jammed phase below the jammed phase, and we may have a fragile phase, which is a metastable or unstable phase. So there are another critical point here, phi c, below the jamming point. So you can imagine, so this stress that the fragile phase has a strong anisotropy. At least when we use the pure shear situation, the force chain appear only in this direction, compression direction in fragile phase. And in the shear jammed phase, we may have an isotropic force chains to sustain the external force. That is characterization by them. But we still have a discussion about what is fragile phase, what is the shear jammed phase, because this is only the picture, and it's not well defined, at least.
Well, you have done a little bit more beyond.
Yeah, of course. And so, and recently, such shear jammed phase might be related to the discontinuous shear thickening. Discontinuous shear thickening is very drastic process to have such protective vest and used for the vehicle suspensions. Anyway, the thickening is the increment of the viscosity as the shear rate increase, but discontinuous thickening has discontinuous jump of the viscosity. And this is one of the simulation for the corridor suspension, which has more than 10 times the shear viscosity larger than the in the lower shear rate regime. So there is a discontinuous jump, and this is our simulation with Michiotsky, which has also the discontinuous jump of the viscosity of the shear stress, and there is a nice hysteresis here, which is very similar to the first order phase transition. And so discontinuous shear thickening is one of the drastic process to have rigidity, because this shear stress might be related to the rigidity, and you can imagine that extrapolation of this branch to reach the finite yield stress. So recently, some people have talked about the relationship between the shear-jammed phase and the discontinuous thickening. And this is one of the results by the 3 years ago. So the CST means the continuous thickening, and this blue line is the onset of the DST, discontinuous thickening. So this paper proposed that the critical line between the CST and the shear-jammed phase is nothing but DST. However, this is not consensus. I think at least the Chicago group proposed a very different phase diagram like this. So this is a shear-jammed phase, and the shear-jammed phase exists here, and the DST has a finite area to have a pitch.
So in the 2015 paper, they said it's just that line.
Just line, and this is an area. So, and I'm not sure, maybe Bulbul knows the more recent consensus in the community, but at least most of the people are confused by these two different pictures. So, and at least, we can say that the shear-jammed phase is related to the DST because both are, shear-jammed phase here, and the DST is a boundary of the shear-jammed phase. Even in this case, DST exists below border of the shear-jammed phase. So that is.
So that was shear rate backing fraction, right?
Yeah.
The fall. So is this just the two-phase opening up? Oh. Like if I have a two-phase coexistence of a line, if I think of tau and gamma dot as conjugate variables, is this just the opening up of that coexistence line?
I don't remember the detail of the experiment setup.
I'm just saying, are they inconsistent, or is it just that blue line? It's like a pressure temperature and volume temperature, right? Volume.
Yeah, that is a volume and the shear rate. And so the phase is a little bit different because this is a shear. Oh, sorry, this is a stress. So the drawing is a misreading to invite some confusion. So anyway, this is based on the pressure control experiment, and the previous one is based on the rate control experiment. So both are based on the different situations. So that also invited some confusion among the researchers. Okay, so so that is the background and the motivation of my research. So I would like to solve some confusion to understand what is a shear-jammed phase and what is a fragile phase and what is this DST. And so this is based on the collaboration with Michio Otsuki, and we have published recently the paper in the archive. So you can read this paper for details, even during talk. Okay, so unfortunately, we don't have any theory to explain the numerical result, but we have a definite picture to explain the mutual relations between the among the some phases which I mentioned. So, before starting the main part, I'd like to indicate the role of the mutual friction between the grains again. So you can find that is storage modulus and against the volume fraction. So in the 2D simulation, so you can find that the red one is a frictionless grains, and the blue one is a very, very small friction between the grains. So that is completely different, you can find. So if we have introduced the very tiny mutual friction between grains into the minus force is a physically small friction between the grain, so which implies a discontinuous jump of the storage modulus. So what I want to say is if we have mutual friction between grains, everything has been changed completely. So that is one message for this slide. And so now that we can tell you the setup of my system. So basically, we have analyzed dense granular materials based on the DEM simulation, which has a harmonic potential between the grains in the normal contact force. And we have also introduced a tangential friction between the two grains. And also we have introduced the Coulomb slip condition by introduction of the microscopic mutual friction coefficient. And basically, we have fixed, we will fix the Coulombic friction constant as one, unity. And typically we have applied such oscillator shear, but we can control the phase of the oscillation. This is a cosine, one of the example of the oscillator shear, cosine omega t, but we can analyze based on the sine omega t or some other intermediate oscillation. And we have an angular frequency omega to characterize oscillation, but we have checked the region for the small omega, in which the behavior is almost independent of omega, sufficiently small omega. And one of the important parameters is the strain amplitude gamma zero, and we can discuss the shear stress. And for example, this is a definition of the shear storage modulus in this case. And basically, we mainly use the system size, which include the 4,000 particles in the system, but except for the very nearby the critical point, we have also checked the behavior is almost independent of the number of the particles because we have also analyzed the 16,000 particle simulations.
And this is 2D, right?
2D. We have focused on the 2D simulation in this part. And, okay.
Shear jamming is normally like there should be higher harmonics.
Okay, so that is important and a good question. So we have initially prepared a very large amplitude, and that this definition of the storage modulus is only valid on the linear response regime. So for the measurement, we will use a very small string amplitude. So I will explain later. That is important point. And so that is related to this one. Yes, actually, initially we have introduced a very arbitrary largeness of the initial strain amplitude, like this. But this might be much larger than the observed strain amplitude. And in a special case, there is no initial amplitude like this. So we have only added small amplitude after the initiation or preparation of the initial configuration of the particles. So, and in the previous slide, I have only talked about the cosine situation, but proper definition of the storage modulus and the loss modulus is given by these equations. And the stress is defined by this one, which is a contact contribution of the Cauchy stress. So
these are now dry grains, right? There's no fluid.
No fluid at present in this part. I will talk on later on the fluid case. So anyway, the theta will be the important parameter to characterize the fragile phase. So that is result of the oscillation. And so if we add a very large, not very large, but we can change the initial strain amplitude like this. And we have measured a very small strain amplitude in the observation. So in this case, if we are interested in the small initial strain amplitude, the storage modulus appeared from this point above the 0.82. So, and if we have such line, however, if we have added larger strain amplitude.
This is the initial strain amplitude.
I mean the initial strain amplitude. And this is the observed final strain amplitude. So in the linear response regime.
So I think, Chandan, the nonlinear is in here.
Yeah, nonlinearity is introduced by this one. So that is true. And so you can find, so as an effect of the nonlinearity in the initial strain amplitude, we may have a different critical density, and which has a shear-jammed phase here. So that is our finding. So at least we can say this state shear-induced jamming.
Very good. Yeah, done. So
Yes.
it's all about the dependence of the storage modulus on packing fraction and the initial preparation.
Initial preparation is very important.
You're telling me that if you go from between whatever your blue curves are, so there are the blue curves which don't shear jam, and then there
No shear jam. Yeah.
Which shear jam.
Yes, that's right.
So you're getting basically two curves.
Yeah.
Right? Because
Yeah.
packing fraction, I have both results from storage modulus at the same initial value of the shear amplitude. These are very different initial conditions. Okay. So
Yeah, depending on the initial condition.
Curve, and in fact, what I should see is that it's values cluster basically. Yeah, I mean, below a certain shear, one curve and below.
Yeah. Can I go ahead?
Yeah.
Okay, so to explain the detail, of course, I expected such questions from the audience. So let me explain what happened in the shear-induced jamming. So the blue line is a linear response for the in the case of the 0.822, which has no rigidity, so around here. So, but anyway, you can find if we have a direct shear without any initial strain, we don't have a rigidity. But if we have such large circle or the large with a very large initial amplitude, we have such stress curve initially. After as time goes on, we can make a percolating network, and after that we can adapt a smaller strain amplitude for the oscillation. Yeah.
But what is your x-axis then? Which gamma is?
Gamma is a strain.
Which strain?
So
the one that you're measuring.
No.
So
that is
gamma not I and gamma not.
Gamma naught is amplitude, and this is basically the gamma naught.
He's kind of
Yeah.
He's achieving at the larger.
Yeah, gamma is in this case gamma naught 1 minus cosine omega t, and we can talk about the gamma there I and the gamma. Yes. Yeah, right. Yeah.
So gamma 0 is what you're using.
Red one. Oh, sorry. Red one.
And so this is at the value of 0.1, which is the.
Yeah, 0.1 is this one.
0.1
The red one.
Is go back. Yeah, 0.01
Is the red one.
Oh, it's one of the blue curves, right? In this.
Blue curve is also this one, but
in your storage modulus versus phi, that's one of the blue curves. Right?
this blue circle corresponds to this one.
Yeah.
Without any initial.
Yeah.
And the red one is?
Red one is this one. So after the large shear amplitude, and we can show and small.
No, it does matter around the initial.
Yeah.
Yeah, the 0.1 does matter. The 0.01 is basically
Initial.
It doesn't matter. Okay.
And this is a direct shear for the blue one. So there is no percolating network at all. So there is no rigidity. However, if we have a large initial amplitude, the situation is very different. So we have a percolating network like this. And after some cycles, such percolating network becomes stable. Yeah, contact. Above the threshold, and we can draw the contact network. And after we adapt a smaller strain amplitude, such percolating network is stable. So that as a result, we have a finite rigidity in the response. That is a shear-jammed phase.
Stress goes up.
Yeah, that's right.
Small hysteresis or something.
Yeah.
Red is a small hysteresis.
Yeah, I'm sure. So, but anyway, that is a typical snapshot of the in the same density, and as a result, as a function of the initial strain amplitude. So in the case of the phi equals 0.82, so if the initial amplitude is very small, there is no percolating network, so there is no rigidity. And this is a critical value, so we may have an entropic. I don't know, but anyway, some percolating network. And
You're showing just contacts, but the color,
color is we have categorized six categories as a strengths of the contact networks. So we have emphasized stiff percolating network to extract the stable structures. And this is a case of the very large strain amplitude, which has almost an isotropic algorithmic network. So that is the algorithmic network in the system. And this is an interesting picture for the strain modulus against the initial strain amplitude. So we can characterize a shear-jammed phase as a memory effect of the initial oscillation. And also the blue one is a result of the theta equals 0. And, And open square is a result of the theta equals pi over 2, which characterizes the phase of the oscillation of this one. So this one is this one, this theta. And interestingly, so depending on the theta, so the beginning of the shear-jammed phase is different.
So theta with respect to what then? What should I think of this phase as being with respect to? Like if theta is equal to 0, theta is equal to pi over 2.
Yeah, so I will show you the definition like this one. So theta appeared in the definition.
Yeah, but then if theta is pi over 2, I just interchange it. Right?
This is what I was saying.
Yeah, that's what I thought, but that's not.
So I wasn't confused about this. Phases that aren't mixing up the
Yeah, so
the conventional definition is the in phase is the storage modulus and the out of phase is the loss modulus.
yeah, but of course the definition that is totally consistent with the conventional definition because usually we can introduce ambiguity of the initial phase of the response outside of the response function. That because this is a time-independent part. So, and so time-dependent part is only, of course, cosine must be appeared in a straight modulus, and the loss modulus must be governed by sine part. But this is a time-independent part. So that phase is important to characterize fragile phase.
So, you're driving initially with gamma 0 initially.
Yeah, gamma 0 I
Is there already a phase theta in there, or is
So
it?
that's what I'm confused about.
Yeah.
Because you're writing a theta in the gamma of t. Forget about g prime, g double prime.
Yeah.
So probably theta appears in one of these. I have two oscillatory functions. The oscillatory function of the initial, strain.
That's right.
And I have the oscillatory function of the probe.
The driving.
Yeah, right.
Theta
Probe.
drives the phase between those.
Phase between the two, or
No. We have adapted the same theta for the probe and the initial preparation.
But then what is theta with respect to?
what? I mean, why should it matter? I mean, that does depend on where my system is. I mean, if you're using the same theta for every oscillatory function, is that effectively shift in time?
But I will show you. So I understand the confusion by the audience. So I will show you the difference between how the theta plays a role in the rigidity. But anyway, that is the observation. And you can find that depending on the theta on this line, the rigidity can be finite or 0 or something like that. So, and depending on the theta, this is a case of the theta equals 0 and the pi over 2. And we have also examined that intermediate case, that's 3 pi over 4. So there is a intermediate response between two extreme case. So that is, so that this region or this colored region may be regarded as, we may regard this colored region as a fragile phase. And we can cover the more larger parameter space by using the controlling the gamma 0I and preparation of the various volume fraction, area fraction. So you can find if the area fraction is small enough, the G prime is 0 for the lower initial preparation of the strain amplitude, and we have a finite response like above the critical initial strain amplitude. But if we are in a jammed phase, we still have a decrease of the G prime, but finally we have a larger stress modulus above the critical point, and you can find such behavior for the above very large volume fraction, area fraction. And we have so far we have only discussed the stress modulus, but loss modulus is very interesting. We had interesting response because the loss modulus can be used. Loss modulus can be used for the characterization of the dynamic viscosity. So, as I said, the system belongs to the enough low frequency regime. So this is nothing but the usual viscosity. So you can find if we are interested in the very dense situation, the viscosity is always very large, has a very large value, but 0.82 or 0.81 has discontinuous jump around the critical value, around 0.1 from this very, very small value to the very large value. So, you can find 10,000 times larger than this branch. So this is very similar to the discontinuous shear thickening in the usual colloidal suspension. So we can also talk about the stress anisotropy in this system. And so this is also the initial strain amplitude. And this tau is determined by the difference between the maximum and the minimum principal value of the stress. So this is a representation, characterization of the stress anisotropy. You can find the peak appear in a shaded region, which is in a fragile region. And except for fragile region, you can find that anisotropy becomes smaller. And that is related to what is the role of the theta. So these are stress strain curve for the theta equals 0 and the pi over 2. And in the case of that pi over 2, we have such stress strain curve. And this region doesn't have any stress. And theta equals pi over 2 is a position, we have after we fix observation, the observation point, observing point is here, located here, no rigidity region. So we don't have any rigidity if we observe the stress modulus in this region. However, if we observe the this region, which is observed in the theta equals 0, you can find the finite slope here in the stress strain curve. So we should have a finite response or to have a finite rigidity. So that is, this state is very different from this state, except which is used for the same strain amplitude and the same density. Density is 0.82 in this case, but anyway, this corresponds to this red curve, and the no response corresponds to this blue data. So that is the.
I'm still confused about data, but I see that we are getting different stress strain curves.
Yes, yes.
Going over, okay, so maybe the difference is that this is the hysteresis curve, right? And it's not complicated. It's not completed over one driving cycle. Is this what you are?
This is a situation for the same as this one, but in the case of the fragile situation, we don't have finite area. Almost this curve and this curve merge to this curve. So, and you can imagine we have such curve, and we may have a shrink to this one.
Sure. So what is the theta?
In this case, so for example, this is a theta equal to pi over 2, and theta over that position can be shifted. Theta equals 0 is here. So position is shifted. Origin, you can find this start from the theta 0, because this is 1 minus cosine omega t. So the minimum value must be 0. And
it's just shifting the max.
Yeah, shifting, yes.
Value of the,
that's right.
The average value of the.
That's right.
So that's not really what this is not how it looks. Okay.
It's cosine theta minus cosine omega t plus theta. Is that what you want to work on? Because then at 0 it will be. But then it will be.
Yeah, so it's shifting the average value of this thing.
Yeah.
From average value of 0.1 to a symmetry.
Yeah.
It's really just shifting
the curve this way.
And the observing point is.
In the strain. Yeah. It's just shifting it from.
Yeah. Observing point is fixed to the 0 point.
And if theta is equal to 0, I'm going from 0 to 0.2. If theta is equal to pi over 2, I'm going from minus 0.1 to 0.1.
Yeah. Okay. So, yeah, fine. I mean, but
so
somehow I did not see this in the way that you've written it, because there the theta is just time of.
I think it's cosine theta minus cosine omega t plus theta. Right, gamma of t.
That is just everything is the same. This one oscillates between 0 and gamma, just with the phase shift.
Yeah. Yes.
No, that's fine. But the gamma, I think, is cosine theta minus cosine omega t plus.
Yeah, maybe this is
So 1 minus.
Okay. We should remove. Yeah, to remove. Yeah, to.
Cosine theta minus cosine omega.
Okay. Yeah, we should remove to avoid the confusion. But this is a perfectly
Yeah, it's really
correct.
changing the range of the strength.
That's right. And if we have a,
Okay, so now
if we have a,
fragile region, it matters.
yeah,
The shear jam region, it doesn't matter.
shear jammed phase, we have such kind of a stress curve. So the observation, the response does not depend on the
Here,
theta.
it doesn't matter.
Yeah, doesn't matter. So that is the main message. And this is how the result depend on the friction constant. So such the region of the shear jammed phase, difference between the shear jammed phase and the jamming point disappear in the case if we are interested in the frictionless case. So that is a one.
So phi c is the fragile?
This is a of course. This red one, theta equals 0. So this critical point. So
Theta
fragile.
0 is phi c, and the theta equal to pi over 2 is phi j.
Yeah. So, and let me draw the phase diagram. We have used the pressure instead of using the stress to categorize the phase. So, as you can imagine that the most important parameter is gamma 0I, and unjammed phase is for any gamma 0I, the pressure must be the 0. This pressure, because of the numerical error, we have set this PTH is very small, but essentially this is pressure must be 0. And jammed phase is, of course, the pressure is finite, which is independent of the gamma 0I. So delta P is a difference between the finite gamma 0I and the 0 initial strain amplitude. And shear jammed phase is delta P
So
is finite.
Something about the size of your distance.
Yes, maybe. And once we adapt such definition, we can draw the such curve. So jammed phase, which is independent of the gamma 0I, of course, by definition, and this is above the 0.8 to something. And you can find the shear jammed phase appeared above the gamma 0I, the 0.1 or something. And you can find the fragile phase, which depends on the theta.
This is from your pressure definition.
Yeah,
But from your cyclic theta-dependent definition, you also have a fragile phase.
Yeah, of course. And so the yellow region can be categorized into the fragile phase. And this thick line is a DST line for the theta equals 0, and the dashed line is a DST line for the theta equal pi over 2. So we can continuously cover the fragile region if as a region observed to have a DST. So we can say that that DST can appear in the fragile phase. Okay. Movie. Yeah.
It changes a lot during the cycle.
Yeah, of course.
Here, it's not clear to me that it's really changing much at all.
So, yeah, it is obvious that if we...
Not deep in the shear jam. Bob cyclic shear into the fragile. Bob didn't do cyclic shear into the shear jam. They couldn't do it.
But anyway, this doesn't have a not large. This had a not large contact number, and this has a large contact numbers. So we can distinguish from the shear jammed phase from the unjammed phase. Yeah. So. I'd like to briefly mention on the frictionless shear jammed state. So there are many papers on the frictionless shear-jammed phase. But I'd like to say that all these states are not stable, mechanical not stable. So to stabilize the system, we needed to introduce friction between the grains. So that is one message. And also, so let me. Yeah, of course, you have.
One is discussed in our case, we do consider stability of this package with the additional. Even the state.
Yeah.
We also have.
Yeah, sure.
We haven't said otherwise. The one moving work is a little different. Because, and I was for a long time confused about it, but I think we understand. So they're actually looking at densities that are above my limit. And there you do have shear-jammed stress, which are stable.
That is controversial.
So, no, I mean, I share your.
Yeah, of course. Yeah.
Because they don't they don't know where.
Yeah, that's right.
I thought they did earlier, we can get it. Yeah.
But anyway, even the Kumar's ruling we adapt a very special.
That is, I think the work that you don't have here, and I had these discussions with Francesco and this, the Greenfield glass community, they claim frictionless hard spheres shear jam.
Yeah, I know. Not the hard sphere. They have very soft, very soft.
No, I'm saying frictionless hard spheres shear jam.
That's the Ginetol.
Right. So they claim they do shear jam. So the Ginetol you're saying is metastable. They don't, from the mean field theory, they say that's not true. So I think that's something that needs to be sorted out. I don't understand.
No, the other authors are Yoshino and
Yeah.
Cody. They've shown in simulations that they do have.
Yeah, they do have a.
Shear jam states which are consistent with the mean field.
I understand.
That's right.
So that's then I don't know how they are unstable.
They have a load very largely overlapped in the system. We cannot reach.
No, the last.
Yeah, last one.
No, that's hard sphere.
Not exactly, I think. Anyway, it's a very, basically, they have also introduced a very, large size distribution to give to reach the very large volume fraction. So it's a very different from the typical situation from which we can
No,
reach.
I'm not arguing with you. I'm just saying there is still this disagreement still exists.
Okay.
And I think we need to sort it out.
Okay. So because I don't have a time, but anyway, I'd like to summarize this part. So jamming is a protocol independent phase. So and shear jamming is a protocol dependent phase. It is a memory effect of the initial stress. So the fragile is a metastable state which depends on the phase of the oscillation. And the DS3-like behavior can be observed in the fragile phase. And the stress analysis becomes the maximum at DS3. That is brief summary. And so, because we don't have a time, I needed to skip this part. But what I want to say is that this is a response for the nonlinear response. And the nonlinear response is very different from the linear response. So in this case, G prime decrease with the initial shear amplitude, but in this case, there is no peak, no decrease of the initial, gamma G prime. And shear jammed phase like phase appeared here. But anyway, I needed to skip this one. If you are interested in this part, please contact me. But let me talk about the brief introduction of the simulation of the colloids by using the hydrodynamic simulation. This is based on the collaboration with my student, Pradabit from Indonesia. We have developed hydrodynamic simulation by using the Lattice-Boltzmann method. Because most of the experiments are used for the colloidal suspension. But so far, we have only obtained the result from the dry granular system. It might be very different. So the LBM is something like that, so that we can include the particles inside the fluid. And such scheme has been developed by the Anthony Ladd some years ago, more than 20 years ago. And so the fluid phase is characterized by Lattice-Boltzmann method, which consists of the streaming term and the collision term, by using the such discrete cells. And particle motion can be characterized by this one, and the hydrodynamic contribution. The force consists of the hydrodynamic contribution and contact and, for example, repulsive force from the electrostatic force. That is standard, and we are interested in the mass density, the momentum density, and the momentum flux or something like that. And to treat the lubrication and the contact force, we have used this one. This is a conventional treatment of the lubrication force between the two particles. We have a fluid nodes and boundary nodes stable to have if we have a finite gap. But if the gap is very close, so we needed to adapt a different scheme to have to introduce to use the table of the resistance matrix formulation developed by the Kim and Carrier, which is a famous textbook. And so we use an analytic expression to characterize very narrow gap for the shear node. And of course, contact, we allow the contact because of the introduction of the two contact space, two radius. One is a contact radius, and another one is the hydrodynamic radius to avoid the singularity at the hydrodynamic surface. So the contact force is characterized by dE. That is the outline of the simulation. And this is our simulation result of the shear, steady shear. We can recover the discontinuous thickening like this, and you can find the contact force dominate above the critical point. So this discontinuous jump is dominated by the contact force between the grains. And also you can find the stress anisotropy, eigenvalue of the stress anisotropy has a sharp peak around DST, so which is expected by the Bulbul. And you can find that decrease of the stress anisotropy in the upper branch and the lower branch. And we have also used the same situation like this. So we have stretch modulus and loss modulus. Unfortunately, in this case, we cannot use a linear response or to adapt a small strain amplitude of the observation because fluid flow removes such contact, so the memory effect disappeared because of the existence of hydrodynamic interaction between the grains. So we should use this expression for the nonlinear response, which might be the controversial or the validity of the argument. So that is the result of the simulation. So that we have a sharp increment of the G prime stretch modulus, And this is also the loss modulus. Loss modulus also the increase as the against the gamma naught. But this is a continuous change. It is contrast to in the previous case, because this is an oscillatory situation. So this is a steady situation. So, okay, I will stop later. This is a discontinuous jump, but the oscillatory case, we have a continuous increment of the viscosity. But if we are only interested in the contact contribution of the viscosity, we have a discontinuous change from 0 to the finite value like this. So again, even in the oscillator shear, the stress anisotropy has a sharp peak around the critical point of the DST and appearance of the stretch modulus. So the very brief explanation. I'm sorry for the very brief and rapid explanation of our simulation of the colloidal suspensions. And as we expected, anisotropy becomes maximum at the DST and the appearance of the order. And the linear response protocol cannot be used in this model. And the viscosity is a continuous change for the oscillator shear, but its contact part is discontinuously changed. Okay, so let me conclude my talk. So mainly, we have summarized the result in the main part. So shear-jammed phase is the protocol-dependent situation, process. And the shear-jammed phase is a protocol-dependent state. And the fragile phase is a phase-dependent metastable state. And the DST-like behavior can be observed in the fragile phase. And see this paper. And this is a very brief summary of the simulation of the LBM, but it's a bit too brief, so that I didn't have time to talk about the detail of this part, and I skipped this part. But I want to say that linear response is different from the nonlinear response. And let me repeat the collaborator. So I would like to thank the collaborators Michio Otsuki and Daisuke Shima and Pradabit, and thank you for your attention. Thank you. Okay.
Do you consider Brownian motion or like how?
No, in this case, we don't introduce any Brownian motion. So instead of the Brownian motion, we have introduced a electrostatic repulsive force. So to stabilize the suspension, we needed to introduce this or Brownian motion. The role is very similar. If we have introduced the Brownian motion, we don't need this one.
I mean, the liquid essentially, it's the collisions of the lattice velocity points with the sphere-induced, if you like,
yeah.
As it is in real life.
Yeah, real life, we must have both. And maybe this is more dominant in many experiments.
So how is this different from the Morris, the Seto, Roma?
They have used the Stokesian dynamics.
Oh.
I have used the LBM. They're almost the same. At least the result is very similar to what they observed. And they have not discussed the oscillatory shear.
They have not discussed?
Oscillatory.
No. Yeah.
That's right.
Chandan, did you guys do any oscillatory shear experiment?
No, I'm fine.
Yes.
You said the shear-jammed state is also protocol dependent? I thought fragile state is, but...
Yeah, of course, fragile state strongly depend on the protocol.
What do you mean by the shear-jammed?
Shear-jammed phase is a function of the gamma 0I. Gamma 0I is a memory of the initial strain amplitude. you know. Yeah, that one or that one. So gamma 0I is the initial very strong.
Yeah, but that just forms your contacts. That I would
Yeah,
call that protocol dependent. That's just like in the DSP, you have the fraction of contacts increases.
Yeah, maybe.
Shear stress.
But
I could replace this by an emission stress.
of course,
I don't know if I want to call it protocol because there is clearly what you're doing through the gamma naught is creating contact.
yeah. Sorry. To introduce the initial contact, we needed. I would say to introduce. We needed.
But I don't know if I want to call that a protocol. It's a non-equilibrium. It's a parameter that's usually thought of as a protocol, but it's not. If you do
Okay.
the same gamma naught, you get the same.
Okay. I agree.
Yeah.
Okay.
Do the same gamma naught by pure shear, or simple shear, or whatever, and you'll get
Okay. I agree.
And we know that there's a scaling of this with the packing fraction.
Okay.
I don't think, because in the DST case, right, it's the whole theory is based on the fact that with an imposed shear stress, you build up the number of contacts.
Yeah.
It's the same thing here. If you look at this fraction of non-rattlers, it will depend on your gamma naught I.
Yeah.
So I don't know if I want to call that protocol dependence because there is a clear thing that's not hysterectic, which is your fraction of non-rattlers.
Yeah. Okay.
That is that is one number given a phi and a gamma naught.
Okay. Maybe my usage is wrong.
No, I'm just saying.
Okay. Thank you for your comment. But what I wanted to say is only the state depends on the initial strain amplitude, and that is.
Yeah, but that's your axis on your baseline.
Yeah, that's right.
And so again, and then
Thank you very much.